Okay, in this presentation we are going to look at the Poisson probability distribution. So this is a worked example, and our scenario here is cars that pass along a certain point on a road over the course of a day. How many cars? During the day, cars pass along a certain point on a remote road at an average of 1 per 20 minutes. Okay, so for example, 3 cars per hour on average. Calculate the probability that in the course of 1 hour no cars pass. Calculate the probability in the course of 30 minutes that exactly 4 cars pass. And calculate the probability that at least 2 cars pass in 30 minutes. Now, just recall that you're not explicitly told that this is a Poisson distribution, so you have to just sort of rationalize it yourself, and in fact provide some sort of a justification for it. Here, the Poisson distribution models the number of successes or events per unit space, and here the unit space is the various time periods of traffic on the road. So it's the half-hour period or the 1 hour period on this stretch of road, and how many cars pass a certain point in time. That is the number of successes. So we have the number of successes per unit space, so that essentially leads us to the Poisson distribution. Now we assume that the rate is consistent from one time period to another, that it's consistent throughout the course of the day. That's obviously not realistic in real life. You know what rush hour is like versus traffic in the middle of the night. But let's just ignore that. We'll just keep things simple, and we'll come to those more complex questions in subsequent statistics modules. So we can model the number of cars passing a road passing a point of the road using a Poisson distribution, since we are dealing with events happening independently over time. The Poisson distribution is characterized by the rate parameter lambda, which is the average number of events in a time period. Now, just watch out if this is very similar to the rate parameter in the exponential distribution. But remember, the exponential distribution and the Poisson distribution are related to each other, but they're not the same. Okay, so in this case, the rate parameter is the average number of events in a given time period. Okay, so forget about the exponential distribution for the time being. Just compartmentalize that. That third bullet point is pretty much correct. Okay, the mean equals lambda, rate parameter, for a Poisson distribution, for a Poisson random variable. So given that cars pass at an average rate of 1 per 20 minutes, the rate lambda is 1 car per 20 minutes or 3 cars per hour. Okay, or it might be 1.5 cars per 30 minutes. So there's our little probability density formula there. Probability of x equal to k, where k is the number of occurrences, equals the exponential of minus lambda times lambda to the power of k over k factorial, where k is the number of occurrences that we are looking for. Correctly, I should put in k greater than or equal to 0. Okay, just to sort of specify the support. Now, so the first question, calculate the probability that in the course of 1 hour no cars pass. So here, for 1 hour, the rate parameter is the expected number of cars, and that is 3 cars per hour. Okay, so lambda is equal to 3. So we use our formula there, probability of x equal to 0. So here we have to do a little bit of calculator work. So the exponential of minus lambda, which is the exponential of minus 3, that's one part of it. Lambda to the power of 0, which is 3 to the power of 0. Now this is where you recall some of your fundamentals of mathematics. Anything to the power of 0 is 1. Okay, so that really cancels itself out from the equation. Now, on the denominator we have 0 factorial, and this is another interesting result. 0 factorial is also always 1. So we have an expression there that is e to the minus lambda times 1 divided by 1. So essentially e to the minus lambda, e to the minus 3. And we work that out, we get a bit of calculator work, 0.0498. Essentially just short of 5%, 4.98%. Now, probability that in the course of 30 minutes exactly 4 cars pass. So here what we're interested in is x equal to 4. So our k value now becomes 4. But also For 30 minutes, lambda equals 1.5. We expect 1.5 cars for every 30 minutes. Okay, so we have e to the minus lambda times lambda to the power of 4 divided by 4 factorial. So this is a little bit more mathematically complex or computationally complex. So lambda here is 1.5, so their first term on the numerator is the exponential of minus 1.5. The other term is lambda to the power of 4, which is 1.5 to the power of 4. Little bit of calculator work, you should find that to be 5.06525. And k factorial is 4 factorial. 4 times 3 times 2 times 1. 4 times 3 times 2 times 1 is 24. So on the denominator there we have 24. So wrapping it all up, exponential of minus 1.5 times 5.0625 divided by 24. That should be straightforward calculator work, and it should work out to be 0.0842. Okay, so that's the answer to the second one. Now, this requires a little bit more work. Calculate the probability that over the course of 30 minutes at least 2 cars passed. Now, at least 2 cars. Okay? Not 2 cars, at least 2 cars. So that could be 3 cars, 4 cars, 5 cars, etc. So what we have to do is find the probability of x greater than or equal to 2. Okay? So what we're going to use here is the complement. So what is the complement of probability of x greater than or equal to 2? That is 1 minus the complement of that, or essentially using the complement rule, that is the probability of x greater than or equal to 2 equals 1 minus the probability of x less than 2. And the probability of x less than 2 can be broken up into two terms. Probability of x equal to 0 and x equal to 1. Okay, so essentially what we have to do is start off by finding this bit here. Okay, these two terms here, add them together and subtract from 1. Okay, so luckily the mathematics of it are fairly straightforward. Recalling that probability of x equal to 0 means that we have a lambda to the power of 0 is 1 and 0 factorial, which is also 1. So when we look for the probability of x equals 0, essentially all we have to do is calculate the exponential of minus 1.5. And that is 0.2231. Now that's a handy result because we get to use it again very shortly when we calculate the probability of x equal to 1. The exponential of minus 1.5 times lambda to the power of 1, which is 1.5 to the power of 1, which is 1.5, divided by 1 factorial, which is 1. So essentially what we have here is the exponential of minus 1.5 times 1.5, and we have that already calculated for us. It's 0.2231 times 1.5, and that gives us 0.3346. So essentially what we have to do is add them together. Okay, just recall that. And that works out to be 0.5577. Okay, so just add those two numbers together. And recall that what we have to do is calculate the probability of x greater than or equal to 2, which is essentially the complement of that. So it is 1 minus 0.5577, and that works out to be approximately 0.4423, 44.23%. So that's it in summary. Those are the probabilities that we have just calculated there. The probability of no cars passing in 1 hour, 4.9%. The probability in exactly 4 cars in 30 minutes, which is 8.42%. And in the course of 30 minutes, at least 2 cars, which is 2 cars or more, the probability of that is 44.23%, 0.4423. And I think that's it done. Okay.